So before we talk about what illuminated contours are, let's review what a contour is. A contour is going to be where a terrain model is intersected by a horizontal plane representing some elevation. In this example here, we have three of those horizontal planes, one at 0 feet above sea level, one at 50 feet above sea level, and one at 100 feet above sea level. And each one of those is going to leave an intersecting line, which in this case is kind of almost like an oval, where that horizontal plane is intersecting the terrain. These would be our contour lines. The way that we draw contour lines is we basically either connect points of equal elevation or interpolate between known points of equal elevation, such as here's a point of 100, and we know there also must be an 100 between 85 and 120 because we can't get from 85 feet high to 120 feet high without passing through 100. So we can draw contours like this, and it's nice to draw them as a black line. That's a fine way to represent them, but it's not the best way to visualize the terrain. There is a better way. This is documented in several places, including Edward Imhoff, who's a famous Swiss cartographer, in his book Cartographic Relief Presentation. In fact, it made the cover. And what these illuminated contours do is they draw white contours on the illuminated side of the terrain. If we imagine the light coming in from the northwest here, these would be the contours that would be hit most directly by that light. And then on the non-illuminated side of the terrain, the one that has a greater angle away from that illumination vector, black contours are drawn. So the white contours are on the northwest side, going off to the north and to the west, and the black contours are on the southeast side, going off to the east and to the south. This is basically just based on the angle between the illumination vector and the aspect direction. The greater that gets, the thinner the lines get, and the closer the aspect direction gets to lining up with the illumination direction, the thicker the white lines get, or on the other side, as they start lining up once again, they go beyond 90 degrees and start better aligning with each other, the thicker the black lines get as well. This is Tanaka's famous map of illuminated contours, or sometimes called Tanaka style contours. And we can see that it really does give an interesting three-dimensional effect by putting the white contours on the illuminated side of the terrain and the dark contours on the non-illuminated side of the terrain. And zooming in, we can see that in a little more detail. Here's the non-illuminated side, the black contours here. These are the contours that are facing off towards the northwest, and they get the white coloring. And it's all put on a kind of medium gray background in order to make sure that both the black and the white are equally visible. So how can we do this in GIS? Well, we could start out with either an aspect grid or a hillshade grid, and then we could reclassify it so that we just get a certain number of classes. Let's say 8 classes, 4 for the illuminated side and 4 for the non-illuminated side. We could then take those polygons and intersect those, or once we've reclassified them into a grid, then we change that grid into polygons, and then we would use those polygons to intersect the contours and pass along that information about their aspect direction to the contours themselves. Then we just apply different line colors, white or black, and different thicknesses of line, white and black, based on which direction the terrain is facing. And then we just take off all that background and put on a plain gray background. We take off the aspect or hill shading map and put on a gray background, and now we have the final illuminated contour map. And of course, to this, we could also add hypsometric tinting or colors based on how high the elevation is, such as this map on the cover of this journal.